high-end women's purses and shoes. You know how much those things cost? I know, because I've got a wife. And I know what those things cost. How do you know when you go to Neiman Marcus in the Galleria that that's real? I mean, it's real, it exists, but how do you know it's authentic? How do you know? It looks authentic. Well, the fake ones look authentic too. So what happens is, because you can make a purse in Milan, by the time it gets to Houston, somewhere along the way the box has been opened. And they've put Vietnamese things in, and they've taken the authentic ones out, and you never know. You could put these little markers in there that authenticate it in Milan, so that when it gets there, you just look at a little sensor, you put it on a smartphone, and it has to have this little tag that gives you the fluorescent spectrum that matches. You would know. Okay, let's get started. So graphene is a single sheet of graphite, and from this, hypothetically, you could cut out something and roll it up and get a C60, or you could cut out a ribbon, and roll it up and get a carbon nanotube, or if you just stack up lots of these sheets, you get graphite. And it turns out that if you're less than 10 layers of graphene, it's considered graphene. Once you hit 10, it's considered graphite. That is an arbitrary definition made by people, but the reason for that is when you hit 10 layers, it essentially it's electronically like graphite in its behavior. When you start getting less than 10 sheets, it looks more like graphene. Stacks of graphene, all right? And the more, if you have a single layer, if you have just a single layer of graphene, it will have certain optical and electronic properties. You put 2 layers of graphene together, it starts moving toward graphite in its behavior. This conductivity goes up, and its optical properties change. Again, this is going to depend on how these are aligned with respect to one another. So, you can have like this, and you can have it totally over it, so that would be like an AA stack, where they're totally the same. But if I just move like this half unit, that'd be an AB stack. And then you can get all of these different patterns as it goes around. These are called the moire patterns that you would get as you start moving these around. Okay, so there are ways to convert graphite into graphene. One of the ways is do a liquid exfoliation. So you take graphite and you sonicate it with different liquids, and these liquids will move their way in between the sheets and begin to spread it apart, because you want to separate graphite layers into graphene, the independent ones. That doesn't work very well. You usually get graphene, it's called graphite nanoplatelets. It's very hard to get less than 10 layers. You can, but your yield isn't very good. Another way is you go ahead and you oxidize it. By an oxidation, you'll cover it with, say, carboxylic acid groups here in the oxidation, and it ends up getting a lot of holes in it, so it's kind of a defected sheet. Another way is you grow it directly on silicon carbide. So you take silicon carbide and you heat the silicon carbide up to about 4,000 degrees. Carbon will precipitate to the top. It'll move to the top. So every silicon has a carbon, but it'll move to the top, and you get this layer of silicon carbide, of graphene on top of silicon carbide. And another way is chemical vapor deposition, where you take a flat substrate like copper, and you flow in methane at 1,000 degrees. And what happens is when those methane molecules hit copper at 1,000 degrees, the carbons will stick, the hydrogens will come off as H2, they'll start breaking off as H2, and you get carbon atoms moving across the surface at 1,000 degrees. So the carbon atoms will be moving across the surface, and then they will start to assemble into graphene, and that's how you can get a sheet of graphene. It's called carbon vapor deposition. A lot of this has been done at Rice. Rice so right here, a lot of this type of research has been done. These have different properties. So remember, nanotubes could have a high mobility, and you remember we had the different ways we could roll up a nanotube. They can have a high mobility, meaning that how fast can information travel through a nanotube, whether it be an electron or a hole, meaning a cation. You can have electrons or cations moving through these. Just to give you a ballpark number, silicon is about 2,000 centimeters squared per volt second. So this is a unit of measure of distance. Silicon is about 2,000. We usually think of silicon as being an amazing semiconducting material with high mobility, meaning you can move information in and out. Carbon nanotubes can have higher than that. Graphene theoretically can reach 1 million. So you go from 2,000 to 1 million. That's why a lot of people were really interested in this from an electronic standpoint, because now you could have theoretically very high mobility, so your computers would work faster. The slow step in computing is not the switching. The slow step is moving your electrons from one device to another. That's the slow step. The switching is actually faster than the movement of the electrons. And that's why you want to have memory, on-chip memory. In other words, you don't want your memory always far away, because now you have to move information back and forth from memory into the logic chip. So you always have some onboard memory so that your distances are very small. Now, nobody has ever achieved this in graphene. People have achieved, probably 20,000 or something, 30,000, 50,000 maybe, but 1 million nobody's ever achieved it, but theoretically this is what it should be. If you cut this down into nanoribbons, this would begin to open up a band gap. So this is pseudo one-dimensional, this is two-dimensional. If you make a ribbon, this would be one-dimensional again. This was first discovered in 1962 by Boehm, who just passed away recently. He discovered this and he actually called it graphene. He named it graphene. However, it was rediscovered many years later, and he even has pictures of this, these scanning electron micrographic images of this. He has this, and this was in 1962. He reported this. Now, it was rediscovered by Novoselov and Gayam. Novoselov and Gayam. Novoselov was the postdoc. Gayam was the senior professor. This was at the University of Manchester in the UK. They rediscovered it in 2004. And these two guys got the Nobel Prize for the discovery of graphene. Well, why didn't they give it to Boehm, who really discovered it in 1962? They just didn't know about Boehm. They only know what their graduate students bring to them to the committee, and they didn't realize this. And so, but what Gayam and Novoselov did is they discovered really the amazing properties of this. Now, Boehm should have received the Nobel with it, and it probably was not real good that he didn't get it. But the Nobel Committee doesn't go back and say, well, we made a mistake. I mean, that's it. The way they did it, they took a piece of graphite. So what Boehm had done, he took a piece of graphite and he chemically oxidized it, and that moved away the sheets. You oxidize it, you get carboxylic acids on there, you cover it with anions, and they'll all start repelling each other and move apart. And it's kind of defective. What they did is they took a piece of graphite and they put Scotch tape. They put it between two pieces of Scotch tape and they pulled it apart. And so it got thinner. And so then they put another piece of Scotch tape on there, pulled apart, another piece and pulled it apart. And the story they tell is they didn't even notice anything and they threw it out. And then Gayam was walking by or something and he noticed. And if you take it and you hold that sheet of that piece of Scotch tape there, you can see a very faint pattern. And so they were actually shearing off sheets. They didn't get individual sheets, but they got few layer graphene this way. And they characterized it, and it was amazing. It just took off because of its amazing electronic characters. Not only this, why as a single sheet is it stable? Remember, we talked about stability. It's stability at that level. Normally, if you take material and you go down to a single atomic layer, it won't even stay together. But this stays together. You can float this up on water. We've done it many times in my lab. I can't see it, but if you have young eyes, you can actually see it. And you can, if you look at the proper angle, you can actually see that single sheet floating on top of the water. And then what you do is with like a silicon wafer, you go underneath it and you pick it up. So what you do is you grow it, say, on a copper substrate, and you put that copper substrate into an etchant solution that dissolves the copper and leaves the graphene. So the graphene will float at the top. And so then you can kind of put something under it and skim it up and get it off that way. Now, if you do that, generally the graphene will rip. It'll rip apart. Just the contact forces on top of the water are enough to rip this apart. Because at that level, it's these forces are quite large. So if this is your copper substrate, you grow your graphene on your copper substrate, and then you put another layer of polymer on top of this. Now, so that supports it. Now you dissolve away the copper layer. You put it in an etchant. Now your graphene is bound to a polymer. And so then what you do is you put this in a beaker of acetone, and that will dissolve away the polymer, and then this is left floating on top of the acetone. Water has these very strong contact forces that allow insects to land on it and stuff that many other organic solvents don't have. So let me tell you a bunch of stories about graphene. There's so much been published since 2004, the discovery, and these guys got the Nobel Prize, I think it was in 2010 in physics for the discovery of graphene. This guy in Novoselov, Boehm never got it. These are graphene quantum dots. The yield of graphene, the cost of graphene quantum dots was $1 million per kilo. Coal is less than $100 per US ton, and we found that we could make graphene from coal in one step in about 25% yield. I mean, isn't that amazing? We had this meeting in my office, graduate students sitting around, and I had a piece of coal, and I said, I bet in coal there's graphene. There's small pieces of graphite that coal, if you leave it millions and millions of years under high pressure, it's going to turn into graphite. And then if you put it under extreme pressures, the thing will turn into diamond. So there must be some en route to graphite. And if you remember your oxidation chemistry from organic chemistry, if you recall organic chemistry, if you took it, if you have a benzene ring, and say you have ethylbenzene, and if you react this with a strong oxidant, the one that's used in your books is potassium permanganate, but there's other oxidants that can do this, like nitric acid. Nitric acid can do this, is that this will go to the carboxylic acid. It'll just burn off this carbon over here, and it'll bring it right down to the aromatic carboxylic acid. And so I told them, take this piece of coal to the lab and just dissolve it up in nitric acid and sulfuric acid. In a mixture of nitric and sulfuric, 1-to-1 mixture, it should dissolve. And it dissolved. And he didn't, it just dissolved. Graphite doesn't dissolve, but this dissolved. Coal could yield graphene quantum dots, and there's different types of coal. There's anthracitic coal, there's bituminous coal, and there's coke, which is actually a petroleum product. And all of these alkyls just get oxidized off, and you go down to the little sheets of graphene that are in there. So you see, everything dissolves in the nitric sulfuric acid. If you do it with graphite, very little dissolves. But with coal, everything dissolves. And then if you scoop some of these up and you put it under a microscope, under TEM, you will actually see these little graphene quantum dots. So this is a 2 nanometer bar. So this is 2 nanometers or 20 angstroms, tiny little things. And depending on which size you have, they will have different colors. And depending on which type of coal you have. If you start with a bituminous coal and you cook it at 100 degrees, there'll be about 3 nanometers. If you cook it at 120 degrees, there'll be about 2.3 nanometers. And then if you take coke, they're 5.7 nanometers, and anthracite is 28 nanometers. Anthracite is just a coal that has been over time moved more toward graphite-like. It's not quite graphite, but it's got much bigger domains of these sp2 carbons in there. Just a quick reminder, this organization is run totally by volunteers, but we do have to pay for the production work. If you could help us out by going to give.jesusandscience.org, we'd appreciate it, or you can click in the description box below. If you can't give, we certainly understand, but please just give us a thumbs up and click subscribe. Thank you. And so a company was started, DOTS, which is now a public company, and you can see, depending on the size of the quantum dot that you use, these are going to fluoresce. You shine a UV light on them, they will fluoresce at different wavelengths. The larger ones will fluoresce in the red, the smaller ones will fluoresce in the yellow, and then they'll be blue and work their way on up. What's one of the applications of this? So it turns out, they don't do this in Texas, but there are some states where you can buy marijuana in government-approved stores. It turns out not all the marijuana sold in those stores is government approved. So people will grow their own marijuana and then sell it in those stores as if it's government approved. So how can you make it so that you know it's government approved? Well, what you could do is you could just say, okay, on the government approved marijuana, while it's growing, we'll just pour certain graphene quantum dots, a mixture of them that'll have a specific optical pattern into the water, into the soil. It will take up the graphene quantum dots. And so now when you harvest this, it's got graphene quantum dots in it. Now you can just hold up a UV light with a little sensor and you will get a pattern based on the fluorescence of the quantum dots. And that can tell you whether it's the government approved stuff. And you say, well, we'll match that. No, it's very hard to match a particular mixture that you might use. And so it's sort of like a fingerprint. So it can tell you. Another thing is it turns out in China, just the tobacco companies, there's a lot of cheap brands of tobacco that are mimicking the official expensive brands of tobacco. And it'll be packaged and everything looks the same. Well, how could you tell? Well, you could mark it in this way. You can also mark frack water. So you do fracking when you're injecting water into the ground to crack the ground to frack and get natural gas and oil up. What you can do is you can put some of this, just a very small amount in your frack water, and you can tell where your frack water is. So if somebody says, oh, you contaminated my water system in my well with your frack water, you can say, okay, let me see. And you can see if they don't have that fluorescent tag. So it's a tagant for many things. It's high-end women's purses and shoes. You know how much those things cost? I know, because I've got a wife. And I know what those things cost. How do you know when you go to Neiman Marcus in the Galleria that that's real? I mean, it's real, it exists, but how do you know it's authentic? How do you know? It looks authentic. Well, the fake ones look authentic too. So what happens is, because you can make a purse in Milan, by the time it gets to Houston, somewhere along the way the box has been opened. And they've put Vietnamese things in, and they've taken the authentic ones out. And you never know. You could put these little markers in there that authenticate it in Milan, so that when it gets there, you can just look at a little sensor and you put it on a smartphone, and it has to have this little tag that gives you the fluorescent spectrum that matches. You would know. It turns out that's not an easy business to be in, because the stores sort of don't want anybody to know. It's not that the stores are doing anything wrong, but if it's not authentic, then they're out of luck. I mean, they just ordered all this stuff and paid for it, and now they got, and so they're stuck with all this merchandise. So they kind of don't even really want to know. And so it's not an easy business to be in. Anyway, this is where we split the carbon nanotubes. You can take carbon nanotubes and we split them chemically into nanoribbons. So we fill this up with chemicals and we'll split them open. And so you can see these carbon nanotubes. These are multi-wall carbon nanotubes. And the way you know this is because it's got, can you see right there, there's sort of a line in the middle of it? If you see that line in the middle, that is the last tube of which there's no more inner tube. So there's one innermost tube. That's going to give you that line. And then you have these other tubes around it. With transmission electron microscopy, you're looking through the material. You're looking through it. So you see these lines, which are the different layers. Even though it's like this, you're looking straight down from the top and you're seeing the lines there. And you, just with the potassium permanganate, it'll open these up to ribbons. If you sonication cut these, you can see there's 1 nanometer, so that's one sheet high, because that's the graphene oxide. Now here's 2 sheets on top of each other. So here's the line where you're going across. You go 1 nanometer up, that corresponds to that. And then when you hit these 2, now you're 2 nanometers high. That corresponds to that, because that's the AFM tip, which runs and it rides right on the van der Waals radii of these things, and it just tells you height. It's very good for height information. And so you can see these ribbons, we can just line them up. You take a paintbrush, you put a silicon wafer, and you can't see anything. You just put a little of the solution and you paint it with a brush, like from north-south or south-north. And so now you've aligned them, and then you just run the SEM and you can see these graphene nanoribbons. We've learned how to also split them using sodium-potassium alloy, which keeps them as graphene rather than graphene oxide. And we've done lots of things with this. We've coated surfaces with this. We were giving a presentation and Lockheed Martin saw this. And so this is now, it's transparent. And now to give you an idea, this is ITO, this is indium tin oxide on your smartphone. And that's what makes this conductive. And that's why you can run your finger up and down. Normally glass is not conductive. That's what makes it conductive is the indium tin oxide on the surface of the glass. Indium tin oxide absorbs about 10% of visible light in the middle of the visible spectrum, which is 550 nanometers. It'll absorb the visible light. So if you were to take a piece of glass that didn't have indium tin oxide and put it on a piece of white paper and take another one of these that has indium tin oxide on it, right next to it, you would see that the indium tin oxide one it's absorbing some light. Our eyes are good enough that it sees that 10% absorbance of light from the indium tin oxide. For this particular layering of graphene nanoribbons that we sprayed on there, it is absorbing 50% of the visible light. And normally the measurement is done right there at 550 nanometers, so it's absorbing about 50% of the visible light. So not as good as ITO. You wouldn't want 50% absorbance of light. 10%, you could still see the thing. But we showed we could de-ice with this. So you could take glass, and since this is conductive, you could apply a voltage across it. It would heat up, and there this ice has fallen off it. So this is ice. This is at a very cold temperature, minus 20 degrees C environment. That little pad is a thermocouple that was taped to the back side of the glass to be able to measure the temperature. And then we were giving a presentation, and Lockheed Martin saw this. So Lockheed Martin builds spacecraft, and they build all these sensor systems for ships. And these are radomes, all right? These are radomes. In here is your radar, all right? The radome is the dome that goes over the radar. It is usually made out of something like alumina, because if you made this out of metal, your radar wouldn't be able to get through. So you need a radome that's made out of something that the radar could go through. And you see radomes all over these Aegis cruisers. The front tip of an airplane, that's a radome, that's where its radar is. And when those get iced up, it's a real problem. It's a real problem for the radar. So what they do is they heat these things up. Well, how do you heat up alumina? Because it's an insulator. They have infrared heaters inside just blasting huge amounts of energy at this just to keep them de-iced. So when they saw this, they said, hey, if you can spray on these graphene nanoribbons and de-ice with these, we could de-ice radomes, because these are so thin it shouldn't obscure the RF. And so that ended up working. Another thing we did is we put these graphene nanoribbons inside of plastics. Did you know when I was a boy, when I was 10 years old, you couldn't buy Coca-Cola in a plastic bottle? Did you know that? Everything was a glass bottle. And it wasn't until I was in graduate school that you could start buying Coca-Cola in a plastic bottle. And you might say, well, why is that? Did you not have plastics? We had plastics, but they didn't know how to, the plastics leaked the carbon dioxide. The carbon dioxide would go through. So you'd carbonate the drink, and by the time you brought it home, there's no more carbonation in there. So it would diffuse through the plastic. Small molecule CO2 diffuses through the plastic. And in fact, they didn't even know how to blow the plastic bottle with these 4 little nubs on it, or 3 little nubs, or 4 little nubs, so that you could put the bottle down. So they would just blow it, and it would have a rounded bottom, and then there was a sort of a cup-shaped black plastic that this went into. So you bought the plastic bottle that had another cup shape of plastic on it, and you talk about the amount of plastic that went into these things, and then you could start buying Coke in a plastic bottle. Because they didn't want people to have glass bottles at ball games, because people get kind of wild. And so they would sell Cokes and beer in paper cups. That's it. And so the guy'd be walking around, and he'd have a bunch of beer, or he'd have Cokes or something walking around, and you'd buy it in a paper cup. They figured out in the plastic, if they put nano clays in there, they put thin layers of clay, that could stop the carbon dioxide from getting out. And that's what they figured out how to do, like when I was in graduate school. About your age, they figured this thing out. And so you could start buying it. So now the CO2 has this tortuous path to go through. Now, this wouldn't last 6 months, but it keeps it in for a couple of months. And it's good enough because Coca-Cola sodas are generally consumed quite rapidly when you buy them. Very few people store them on shelves for a year. From the time it's made to the time it's sold is only a matter of like a couple of days. And then people get it and they consume it. And so it was fine. Maybe 10 years later, before you could buy beer in a plastic bottle. You're like, why didn't they just put the nanoclays in the beer thing? Because I don't know if you've ever smelled beer that's been spilled on a carpet after a couple of days. When I was in school, the drinking age was 18, and every dormitory, it smelled like a wet dog. And that was because beer that was spilled all over the ground, and it smells terrible. Has anyone ever spilled beer after a few days on a carpet? You've never done that. You should try an experiment. It really stinks. The CO2, they could keep the CO2 in with the nanoclays, but CO2 is 3 atoms large. There's carbon dioxide. There's another molecule, O2, dioxygen. Oxygen from the outside could get in, and then you'd open the beer and it would stink. So they couldn't figure this thing out. So it wasn't until they got really good with the nanoclays and made them thicker that you could start buying beer in a plastic bottle. So for many years, beer was only sold in glass bottles for that reason. And so, why did I tell you that story? Because it's interesting. But this is what we did, is that we put graphene nanoribbons to make a really tortuous path for molecules to get through. And so this could get in because it's a smaller molecule. This couldn't get out. And so it took them a long time to figure this thing out. It turns out we looked at nitrogen, which is a small diatomic molecule, and nitrogen diffusivity. And so you pressurize this system and you look at how well it holds in the pressure. And so it turns out that we could make it so that it holds in the pressure really well. All these other ones were leaking out. And so if you just use graphene oxide, which people had used, you could get an 80% decrease in nitrogen diffusivity through the plastic at 3 weight percent filler. If you use nanoclays, you had to use 14x decrease, with 28% filler. So there's a lot of inorganic clay in those bottles, keeping that CO2 in and keeping the oxygen out. With the graphene nanoribbons, we could get 1,000x decreased with half a weight percent filler. So that's a big advance, you see? Because what happens is you got to keep gases from getting into plastics under high pressure. So if you have a blowout preventer, this is this big hunk of rubber, which we talked about last time, that holds this pressure in oil wells, or even just a seal, a rubber seal. What happens when the pressure is very high, the gas diffuses into the rubber. And then when the pressure is released, that gas is coming out of the rubber. And it comes out very fast, and it blows the rubber. It's called explosive decompression. And it blows out, and it blows out your seal. And if you lose a seal when you're doing oil recovery, if you lose a seal underground, you have to shut that thing down, and it could be like $100,000 a day just downtime, let alone all the time to pull up the metal casings and put in a new rubber seal. So just a rubber seal. You want these things to be able to keep the gases from getting into the rubber. Here's an important question. Why would anyone believe that a man named Jesus died and rose from the dead? If you don't believe in the physical resurrection of Jesus Christ, send an email to tour@drjamestour.org and we'll set up a meeting, and I will tell you about why I embrace the resurrection of Jesus Christ. Okay, so we filed multiple PCT applications. In a lecture or two, we're going to talk about what a PCT application is. It's a patent application, what PCT means. Then this was licensed to another company, and then to another and another company, so it's made the rounds. And this is, remember this rat I showed you? Remember I showed you this walking rat, this rat where we put the graphene nanoribbons in its spinal cord, totally cut in two spinal cord. This is what we put in it. It was the graphene nanoribbons as a 1% solution in polyethylene glycol, totally cut into the spinal cord. We didn't do the surgery. The surgery was actually done in South Korea. And then you put these graphene nanoribbons in there, and you get the growth from top to bottom, bottom to top, and that mouse, that rat, starts walking around. Again, scored 18 out of 21 after 2 weeks, after the brain remapped the connections because they weren't the same anymore. And then after 3 weeks, she's doing really well. And you see her after 3 weeks scored a 19 out of 21 on mobility. Now, remember I told you could grow graphene on a copper substrate with putting in methane gas, and the molecules of methane hit? I mean, isn't this interesting? You didn't know how to make this stuff 5 minutes ago, and now you have all these ways to make graphene. And so people were growing it with just this gas, and then it turned out my students did it with just solids. So they coated polymethacrylate on top of copper, and you just heat it up to 800 to 1,000 degrees. All the excess carbon comes off, and you grow very nice monolayer graphene. And so I was contacted by a PMMA company from Japan that makes PMMA because graphene just sells for so much, and PMMA is cheap, polymethyl methacrylate. But then we realized I told the students, just try it with other types of you probably don't even need polymer, just try sugar. This is just sucrose, just table sugar. You get a little packet of sugar at the coffee shop, and you dump it on there, and you heat it up to 800 to 1,000 degrees. Boom, beautiful graphene. So I was contacted by a sugar company because I thought this would be great markup on sugar, because you can take sugar and turn it into graphene. I'm talking about like it was a little piece of graphene, tiny little piece of graphene was like $250. And we're talking about something that weighs, like about 10 nanograms. I mean, like nothing. And we characterized it, and this is what really good graphene should look like. It should have this is the graphitic band, this is the 2D band, and the 2D band fits to a single Lorentzian fit, and you scan it over a whole area. And then I said we can probably grow it from a roach. Now, you try to find a roach when you want one. You can't find it. When you want a roach, you can't find them. So anyway, when the exterminator comes 3 times a year to my home, the next day you usually find a few dead roaches on the ground. And sure enough, there was a dead roach, and I picked it up, and I brought it in, and I gave it to the student. I said, let's see if we can grow graphene from this roach. And the roach itself turned out to be too much, so he just took the roach leg, and he put it on there, and it grows. Now, you have other elements in there, you have things like iron, but what happens is the carbon atoms run across the sheet, and from the bottom, you get really nice graphene from a roach, because it's carbon. You're just breaking everything down to just the carbon atoms. And it turns out we could do it with a cookie, with chocolate, with grass, with plastic, with dog feces, and with roaches. And I said, just get all these different carbon sources. And even, in publications, you have to put where you sourced the material. So for this one, it was my lab manager's dog, and he had a miniature dachshund, so we put miniature dachshund on there, and that's where the dog feces came from. But it's graphene, all of it, it forms graphene, which tells you, this is what it tells you. It tells you that the value of a material is not so much in the elements as it is in how those elements are hooked up to each other. So if you took a human being and you put them on a sheet of copper and heat them up to 1,000 degrees, you're going to get graphene. That's what's going to happen. The value of something is how these are arranged. Now, a human being is worth much more than a sheet of graphene. But what happens is, if we just put aside the spiritual side of the human being, which is without value, just look at the mechanical part. If you wanted a robot that could serve you as well as a person could serve you, how much would you be willing to pay for that robot? Just the mechanical behavior and of this entity, it's worth so much. But if you cremate somebody, boom, the whole thing goes to CO2 and water. What's the value of that CO2 and water from cremating a person? Like maybe a penny? If you were to capture that CO2 and that water and sell it. But you see, the value is in how these are arranged. That's the value of something, how it's arranged. You know, how much would you pay for a camera? But you take that and you burn it, and I'm not going to pay anything for that now. Well, it's the same elements. What's your problem? The elements are all the same. Everything's that. No, it's how those are arranged that brings the value to something. All right, so we made this into thin, transparent sheets, filed a bunch of patents on this. This was licensed to a big company. And that's the way not to make money. You take what you have and you license it to a big company. That's how you take this beautiful nanomaterial, you license it to a big company. I guarantee you will make nano dollars. That's how you do it. And so I'm going to tell you when we talk about starting companies how you do this. You got to start a company around this, and you start working on this, and you then partner with big companies. You don't sell them the tech, you partner with them, and you sign a joint venture so that you own some of that business, that you own part of that business. And then eventually you have now the potential for a liquidity event, meaning that company may buy out your company. That's a liquidity event where a lot of money comes in. That's how you make your money. Or what happens is your company grows and grows and you go public. When you go public, you raise a lot of public money for your company. That's a liquidity event. And then there's a lot of money. Now, the founders of the company are not allowed to cash out right away, or else people will do what's called pump and dump. You know, they'll build a thing up and then there's really nothing there, and they'd have a public company and all this money would come in, they take the money and they run away. The founders, you have to wait 2 years before you can take your money out. But anyway, we did lots of wild things. We took carbon nanotubes that had functionalizations on them and we put it on a copper sheet, and then we grew. And what happens is now you have these nanotubes with graphene between it. So we called it rebar graphene. And so you could actually see these little rebar sheets and these little rebars in there. That's the nanotubes. And so you could see the graphene. There's the moire pattern of monolayer graphene. There it is. I mean, each one of these little things is a single atom. You can actually see the single atoms by high-resolution TEM. And we've got one of the best TEMs in the world here. It was a mere $14 million. And it's on the bottom of Brockman Hall, the physics building, in the basement of Brockman. Here's freestanding graphene floating on top of water with a little bit of butanol. If you were to do this just with graphene, it would tear apart. But this stays together because it has all these nanotubes in it. And if you physically stretch this thing and pull it out, you can see the nanotubes start reaching out. And so here's a nanotube. And from this moire pattern, remember, this is, you're looking down the top, but you're also seeing the bottom. You're looking through this single wall carbon nanotube, and this is the moire pattern you should see. So here's the simulation. So from the simulation, you can tell that this is a 10-4 tube because you see how this has this sort of pattern. If you had a 10-3 tube, it would give this pattern. So from the moire pattern, you can model this, and then you know what type of tube you should have. And that tells you how much this tube is twisted. And the twist in it that made that tube. And you can see this, like here's a carbon nanotube, and it grew right into the sidewall, so it's a mesh of carbon nanotubes and graphene. This is like nanomaterials at its finest. This is amazing. Now, this is where we grew carbon nanotubes vertically off a sheet of graphene. So we characterized this, and so we grew these carpets of carbon nanotubes just on 2 places. So we have a platinum electrode here. We grew we grew graphene, and then we grew the nanotubes vertically. And so this is the top of that carpet of nanotubes. So you get a carpet of nanotubes, but you're looking down over the top, and that carpet is kind of split apart. You know, the fibers have kind of split apart. That's carbon nanotube. You're looking down over the top. And so what we could do is we could take from graphene base to an electrode, so graphene base to an electrode, and measure the current through there. So here's the IV curve of the current. Then when you lift up one of the electrodes, you have now an open circuit. You get no current going through. This is the current voltage curve. And then if you touch the top of the carbon nanotubes, it overlays with that IV curve. That means you lost nothing going from that graphene to the top of those tubes. That's how we knew that this was a very good electrode. And that's what led to that battery company. It has this very high surface area of up to 2,600 meters squared per gram. The way we studied this coming out of the base, so this was a carpet, and then you stick this carpet into a solvent like ethanol and you pull it out and you just get these bunches. And this is like when you go swimming. Your hair may just be hanging down, and then you jump into a swimming pool and everything goes into clumps. You see what I mean? Everything clumps up together where the hairs start coming together. That's exactly what this did. They clumped together. I have 4 children. I have 2 daughters, and my wife used to make ponytails on them. So she would take all their hair and gather it up and make a ponytail. And you're like, why didn't you make their ponytail? Because every time I did it, it was bad. It just didn't look too good. And the girls didn't like it, and my wife didn't like it, so my wife always made the ponytail. So what happens is, if you watch the hair on a ponytail, it actually tracks with the surface, with the scalp. So all the hair is tracking with the scalp, and then all of a sudden it goes up in a ponytail. And so what happens is, when these make these bundles, the carbon nanotubes are running across the surface here, and so you could zoom right in here with the TEM, and you can say, what does it look like at the base where the carbon nanotube is fused to the graphene? And you look at the base, and calculations went before us and said, if you have a carbon nanotube growing from graphene, you should get alternating 7-membered rings to be able to make that turn to go into this. And this is exactly what we could see. You zoom in here, and you could see these alternating 7-membered rings, which are really hard to see on this. But we mapped some of them out. But you could see alternating 7-membered rings. So we knew we had a direct fusion of nanotubes to graphene. This is the way you study it. This is how this is done. And you just have all of these tools. And it's like Christmas. You have so many tools that you can do this. And we made these micro supercapacitors from this. And we made lithium batteries out of this thing. And so this is what led to that company. Just this advance led to this company, Zeta Energy. So if you just Googled Zeta Energy, you'd come up with this. And we filed a bunch of patents on this. And I just took this off their website today. Performance, cost, safety, and how fast they can charge this and everything. It's a great battery. And so they're making these prototype batteries that they're distributing in different companies. We came up with another way to make graphene, which is now the most popular way of making graphene. And that's taking a laser, and the laser that's found in every machine shop. We've got around 10 of them on this campus. Every machine shop, whether you're in Moody, Oshman, every machine shop has one of these lasers, or multiple of them, and they're used to cut wood or laser write patterns. It's a 10.6 micron CO2 laser, very common. You can even buy them for like, I don't know, a couple $1,000s, these laser writing systems. A good one costs a lot more than that. But the student had graphene oxide, and he had put graphene oxide on a polyimide surface, this polyimide surface, which is this plastic, and he went to hit it with a laser. He went to Oshman Design Kitchen, hit it with a laser. He wanted to convert the graphene oxide, blow out the oxygens, convert it back to graphene. He did that, and in the process, the laser missed the graphene oxide and hit the plastic. The plastic turned black. He put it under the Raman analysis, and guess what he saw the plastic turn into? Graphene. Exactly right. No one had ever seen that before. So now you could just take plastic and turn it into graphene just by hitting it with a laser. But now you can write the pattern. So you have this pattern. And so this Universal Laser company gave us this $100,000, like $120,000 laser system, because they thought if we published a lot of papers with their laser system, they'd sell a lot of these, and they did. And so wherever the laser hit, you got the polyimide and you got graphene growing on it. And it formed like a film of a foam of graphene. And you get this pattern. And you see this moire pattern. You can see these moire patterns, and you can see it's sort of a distorted graphene. You can see some 7-membered rings because it forms so quickly. The laser heats this up, and it heats to 2,500 centigrade in a millisecond, and then cools down very rapidly. So it doesn't have time to order into all the 6-member rings. When you grow on copper, this is a slow growth, slow cool down, and so everything can thermodynamically arrange. But when it's trapped now, it's trapped in a kinetic state. And so you get this mesophase barrier where it traps in there. then we can analyze the surface. We've done so many things with this. We published like 30 or 40 papers on this, anti-fouling, electrocatalyst. And when we wrote the patents, we claimed everything in the patents that we could think of to try to do this. And this just turned out to do so many different things. We studied how does it affect the different surfaces at the different temperatures and things like that. And then we could, here's the rice R, and we could grow this. And if we changed the parameters, it would grow rather than a foam, it would grow as these fibrils coming up. And these could even be 1 millimeter high. So you can grow these foams 1 millimeter high. And we just did so many things with this, and we'll talk next time about all the things we did with this. So you'll see how we went from the discovery, then took this through to applications, and then we filed these patents to show all the, claiming all these different application areas, and then you start a company around these application areas. So hopefully you got your inventions in, and if you have questions about the way I graded your last inventions, come and talk to me. I'll be glad to talk with you about that, and we'll move on. All right, see you next time. If you're enjoying this series, give us a thumbs up and click the subscribe button, and that way you'll hear when we're coming out with new videos. There are no salaried employees in this organization. All the accounting, all the legal work, that's all done by friends of mine. The only thing that I have to pay for is the production work, and if you could help us out with that, I'd appreciate it. There's a link below where you can just click on that and help us in several different ways. Thank you.